My name is Grace Fernandez, and this is my black hole lab. In the introduction, I'll go over the overview, equations, models, and brief overview of lab results. The purpose of this Lab 2 is to analyze the star's motion, then find the net force on the star, estimate the mass of the black hole, and in part 2, I will fly around the black hole without crashing on the planet or the black hole. In part 1, I use the equations momentum formula, and I use this to find the net force acting on the planet. I then use Newton's second law of motion to get the net force parallel and the net force perpendicular for the planet. And then I use Newton's law of universal gravitation to find the mass of the black hole. I set the universal gravitation equal to the net force, and then I solve it for the mass of the black hole. The second part, I use an additional formula, which is the position velocity update formula. I use both of these to use the code and update the code. In the top model, the glow script was used to analyze the star's motion to find the net force on the star, estimate the mass of the black hole. This model uses the momentum formula, universal gravitation, and Newton's second law to predict the future location of the object within the given data. In the bottom model glow script, this is the part 2. It was used to fly around the black hole without crashing on the planet or the black hole. This model uses the momentum formula, universal gravitation, and Newton's second law to predict the future location of the object with the given data, as well as the other two equations, which were position update formula and velocity update formula. Second part. Brief overview of the lab results. In the completion of the lab, I was able to calculate the forces acting on the star through the use of the momentum principle. The mass of the black hole was calculated with the universal gravitational formula, which was 1.203991 e to the 34th kilograms. Lastly, I was successfully able to simulate a ship taking off from a planet and flying around a black hole without crashing. The initial velocity I used that was successful, and there were multiple options I could have used, was negative 13e to the 6th in the x vector, and then 9e in the y direction. Primary information, I'll go over the main physics idea, systems, surroundings, initial conditions, details of code, and the outputs. Primary idea, the object's net force is calculated with Newton's second law using the change in momentum over time. The F net is equal to F net parallel and F net perpendicular. The F net perpendicular force is responsible for the change in direction of the star, and the F net parallel force is responsible for the change in magnitude of the star. F net was equal to the universal gravitational force. The primary information, so the system surrounding and initial conditions in part 1, the system was the star orbiting the black hole, and the surroundings was everything around it, including the black hole. The mass of the star was 2.0 e to the 30th kilograms, and delta t equaled 1 day, and other initial values were randomly set by my email. 2, the system was the ship orbiting the black hole. The surrounding was everything around it, which was the black hole and the planet. The ship had a mass of 7.0 e to the 10th kilograms, and the planet has a mass of 9.0 e to the 28th kilograms. The black hole had a mass of 1.203991 e to the 34th kilograms, and the ship's initial velocity that I used that was successful was negative 13 e to the 6th in the x direction and 9 e to the 6th in the y direction. So it's code part 1. The code is a loop that uses Newton's second law to find the force acting on the star. The first, starting with the momentum and using the mass and the velocity, it was easier to calculate the net force using the momentum equation. Using momentum over time, which was equivalent to the net force. For every step of t, the net force was plugged into an equation and printed the black hole's mass. At the end of the program, the code prints out the net force, the parallel net force, and the perpendicular net force, as well as a visual representation of the orbit. The code for part 2, the code is a loop that uses the position update formula as well as the velocity update formula to get the result of the visual representation. It uses the force of gravity from the planet as well as the black hole to get the total net force. By setting the initial velocity, the code runs a highly accurate representation of the movement of both the planet and ship. Initial velocities, I use negative 13 e to the 6th and 9 e to the 6th. Some outputs, so there is the F net and F net parallel and F net perpendicular with all done. Part 2. In conclusion, the possible errors, what ifs, and what does it mean? So possible areas, one area is that the delta t is not low enough, therefore it does not give me the most accurate data. Another possible area is that I missed a syntax error in my code and it was outputting, however, it was not mathematically correct. In my analysis, you should discuss how the net force is and its parallel and perpendicular components are different from the rate of change momentum and its parallel and perpendicular components. So the values are equivalent, however, they are applied to the system in different ways. It is easier to observe velocity rather than acceleration. That is why I calculated the momentum principle first and then in second law to get the F net parallel and F net perpendicular. What if, instead of wanting to take a quick look at the black hole and leave, you decide you want to orbit around the black hole? So what I needed to change with my initial velocities, I needed to set my y high enough so that the ship escapes the planet's gravity, because it's the starting of the orbit, so it needs to be basically straight, but it has to be low enough so that it doesn't fly out of the orbit and it doesn't shoot out and lose the system.